Hello, and welcome to Empowered Learning. This particular lesson will be on what we call marginal analysis. And so when we do marginal analysis, what we're really trying to talk about is the rate of change of such things such as revenue, cost, or profit. We're going to start this particular lesson reviewing supply and demand and how that builds into getting revenue, cost, and profit. And then from that, we will come up with our revenue, profit, and cost equations, talk about what it means to have average revenue, average cost, and average profit, and then from that derive what our marginal cost would be, marginal revenue, marginal profit, and the marginal average revenue, cost, and profit. And then from there, we'll go on and do some simple examples of how we actually apply a marginal cost or marginal revenue or marginal profit in real life. So let's go ahead and get started. So we see here that this is a basic supply demand type of graph. And so, of course, when we talk about marginal analysis of things, we're basically talking economics, and we know everything is run by supply and demand. And so if we start off by looking at supply and demand, we see that our what we call price supply curve is basically saying as our quantity increases, our price increases. Or put another way, the more things that we buy to stock up to be able to sell, the more it's going to cost. Our price demand curve, which is here, is basically telling us, hey, depending on what you sell it for, there's going to be a certain demand for it. And we know that that's an inverse relationship. So basically, when the prices are high, we know that demand is low. And when demand is high, then that means the price is low. So hence why we have this line with a negative slope here. I just did linear curves for both the price supply and price demand functions, just to keep it simple. But these things could be other curves other than just linear curves. So the point I want to make here is that when we talk about the price supply and price demand curves, we see that our price supply is giving us sort of an indirect way of measuring cost. And our price demand gives us a way of measuring revenue. Okay, it's not direct, but it gives us an idea on how our revenue stream will be. And so we see that if we know that our P is equal to price and X is going to be the quantity, whether that's the quantity supplied so that we can sell it or the quantity that's being demanded once it is sold, then we see that the connection here is that revenue is basically going to be the quantity that's sold after we supply ourselves and sell it to the end customer times the price. And so we come up with revenue equaling X times P, or quantity sold times the price. And so from all this, that's the big connection, that revenue is however many we sell times the price that we sell it at. And we get that from this particular graph here. Now, moving on to our revenue, cost, and profit graph, we see here that our cost, which is still in the red, mimics the kind of cost curve that we have here if cost is indeed linear. Our revenue, we know that for a particular demand or particular quantity of items being sold at one time, there's going to be what we call max revenue that we can get from that. And so because of that, we have our revenue here sort of mimicking a quadratic type function, which you'll probably see a lot. And we see that here would be the place where we would have max revenue. The point I want to bring here is that we see that since our revenue curve is parabolic in nature and our cost curve here for this particular example is linear, we see that we have these break-even points. And so these break-even points are places where revenue meets cost, and these two breaking points mean different things. And so I'm going to expound upon that a bit. So here when we talk about our X min and X max, of course, these are the minimum quantities that's made. These are the maximum quantities that's made. Anything beyond this point going to the left, we know that we're losing money because revenue is going to be negative in that aspect. And here we're going to be losing money if we keep on going to the right here because we're losing money in revenue. Of course, with any business, there is an initial startup cost. And we see here that with this y-intercept here for our cost function, we see that that is representing our initial cost. And of course, you need to make revenue to make up costs. So when you're at this point here, this is the first break-even point, which is the point where you've made enough revenue to basically, support your cost that you had to start the business or start the venture or whatever. Now, as we move on, you see that once you get past this first break-even point, you're starting to make money. And so here, that's where the profit region is. And if you notice, after you get to the max revenue point right here, and so this would be the place where a horizontal tangent line for the revenue function is equal to 0. We see that revenue starts to decrease, but we're still making money up until we get to the second break-even point. Okay. Now, this break-even point represents something different. So if you had a business, let's say you've grown to the point to where you've made a lot of money, but now you want to do something like gain market share. So if you gain market share, what you're really trying to do is you're giving up revenue to be able to have more quantity of your particular product out. So this particular area would be what we call the market share area. And as long as you stay within that, you're fine. Another instance where this would be applicable would be, let's say your business is very, very large. So let's say like a Walmart or Procter & Gamble or something like that, where your business is very, very large. It's hard for you to grow year on year. However, you have to operate in such a way because you have so much product, you have to store it elsewhere, you have to pay for shipping costs and all that, and that's eating into your particular profits. Now, of course, you would have to control that so that if you went too far here, of course, you'll meet the second break-even point if you went too far. And so then you're sort of hurting yourself because now you're in a situation beyond this point where you're still making money, but now you're actually losing revenue, okay? And of course, we don't want to be there. If we are over here in this area where we have max revenue to here, this is what's called the growth area, okay? And so my point in saying all this is that, of course, from supply and demand, it depends. We have to play this game with supply and demand to see, all right, well, are we in a growth phase or are we in a market share phase? Or are we a business that's so big that we have to operate within this region here to be able to support all of our customers worldwide, okay? Now, we notice here that here and here we have the loss. And of course, there's the profit. And this is how revenue, cost, and profit are all related to one another. And everything goes back to supply and demand. So now what I want to do is, since we've talked about this and we've noticed that revenue is equal to quantity sold times price, what I want to do now is focus more on what it means to have a revenue, cost, profit equation, define those, and then from there, we'll talk about average cost, revenue, and profit, and then we'll do some examples. So I'm going to go ahead and erase this. All right, so we know that our revenue is just going to be quantity sold times price. And so we could name that function R of X. So if I do that here, if my function is going to be R of X, which is revenue, then I said earlier that the marginal revenue would just be the rate of change of revenue. And we know that to be the derivative. So in taking that, if we have revenue, then R prime of X would be the marginal revenue. And of course, we could also express it this way. In Leibniz notation. For cost, we know that cost is composed of fixed cost plus variable cost, okay, which follows what we were talking about with the supply demand curve. Of course, if we name our cost this, then of course C prime of X would be what our marginal cost would be. Okay? For our profit, P of X, we know that profit would just be whatever money we make, which is our revenue, minus our cost. So if we take the money that we make, subtract from that what it costs for us to make the money in the first place, we have profit. And of course, if we call this function P of X, then the marginal function for that would be P prime of X. Okay, so we've talked about supply and demand and how that feeds into revenue, cost, and profit. So the next thing that we want to do is talk about this concept of average revenue, average cost, average profit. Okay, and so in short, when we say average cost or average revenue or average profit, we're taking whatever it is that we're measuring and dividing it by the quantity of things we're selling. So for instance, for revenue, my average revenue would be the amount of revenue divided by the quantity that the revenue came from. Putting that in symbols in terms of what I have here, we could say that average revenue would be R of X with a line over it, and that would just represent R of X divided by X. Okay, and of course here, whenever we do this particular version of this, we see the X is in the denominator, so X would have to be greater than 0 here. So saying all that to say, if we had average revenue, then we would have to do the average of R prime in order to come up with the marginal function or rate of change of that. And so similarly, we can do the same thing for cost. If we had average cost, so we would have to do C prime of X of C bar, okay? And lastly, if we did profit, average profit, that would have to be the average profit prime, which would be this. Of course, for average cost, this would just be C of X divided by X, and average profit would be P of X divided by X. So in short, that would be what our functions would be. So we've talked about average revenue, cost, and profit, as well as regular revenue, cost, and profit. And so now what I want to do next is, now that we know what these functions are, I want to do a simple example where we take the revenue and cost for something, and from that we form all these different functions from it. So I'm going to go ahead and erase this and do this now. All right, so suppose that we have a revenue function that looks like this. And we have a cost function that looks like this. Okay, so from here, I want to find out what all these different functions are. So I'm just going to go ahead and write them. I want to find out what the marginal revenue would be, the marginal cost, the marginal profit, as well as what the average marginal revenue would be, average marginal cost, and average marginal profit. So before going into this, notice that this particular revenue function has the form of X times P, where this part here in the parenthesis is representing the price. And as you can see, this is a function, a linear function that has a negative slope. So that cost function looks something like this, which mimic what happened when we talked about the supply-demand curve. So you can see how they form the revenue function from knowing the quantity sold times the price, okay? All right, so now that we have this information, let's just go ahead and find out what these functions are. So if we want to find out the marginal revenue, then here what we need to do is figure out what the derivative of R of X is. And so I'm going to go ahead and multiply or distribute this in here, this X in. So we're from here, so if we take the derivative of R of X, we know the derivative of 12X is what? That's right, 12. And so here, the derivative of 0.04 X squared, we know that the 0.04 is a constant, so we leave that out. We multiply this times 2, and then we subtract 1 from the exponent. So this would just give us 12 minus 0.8x. For our cost function, we see that it is parabolic in nature, and it actually looks like this. So looking at this, we'll take the derivative. We know the derivative of 210, which is a constant, is 0. If we take the derivative of 4.6x, that will just be 4.6. And if we take the derivative of 0.01 x squared, that would be a minus 0.02, yep, that's right, x. And so now we clean everything up, and we just have this function. Of course, now that we have revenue and cost, the derivatives of those, if we want the profit, we can just take the derivative of the revenue minus the derivative of the cost. And so we already have that information here, so we can just plug it in. So 12 minus 0.08x minus, and then we subtract all of this and make sure that we put this in parentheses to make sure that we're subtracting all of that. So now from here we distribute. So we have 12 minus 0.08x minus 4.6 plus 0.02x. And then from here we just combine like terms. So here we have 12 minus 4.6, so that would be 7.4, and negative 0.08 plus 0.02, so minus 8 cents plus 2 cents gives us minus 6 cents. Okay, and so that is what our profit equation would look like. Well, the derivative of profit rather, or marginal profit. So we have marginal revenue, marginal cost, marginal profit. So next what we want to do is figure out what the average revenue, average marginal revenue, average marginal cost, and average marginal profit would be, okay? So for these, we would have to do something a little different, because, of course, we know that the average revenue, which is this, would be R of X divided by X. So when we take the derivative of those, it's going to be a little different than just taking the derivative of the revenue, okay? And one mistake I see a lot of students do is when they try to figure out what this is, they will say, I want to do this divided by X, and that's not correct, okay? So we actually have to take this particular function and apply the derivative to it, which means more times than not, you're going to be employing the quotient rule. All right, so let's go ahead and erase this, and then we'll come up with our average revenue and average cost functions, and then from that, we'll figure out what these last three are. All right, so our average revenue would be R of X divided by X. So this would be 12x minus 0.04 x squared, all of that divided by X. And so if we simplify that, that would just be 12 minus 0.04 x, okay? If we had our average cost, then that would be C of X divided by X. So of course that would be 210 plus 4.6x minus 0.01 x squared. All that divided by X. And so this means that we would have 2 over 10x plus 4.6 minus 0.01 x. And of course, if we wanted to do our marginal profit, then this would just be the difference in between R bar of X and C bar of X, okay? Or average revenue minus average cost. And so for here, we could do this one by basically saying this, which is our average revenue, minus all of this, which is our average cost. Okay, and so we'll go ahead and combine like terms for this after distributing. Okay, so now we're here, we will combine like terms. So again, we have 12 minus 4.6, which is 7.4. We have minus 4 cents plus 1 cent, which is minus 3 cents. And then minus 210 over X, okay? And so these are our average revenue, average cost, average profit equations. And so now we'll take the derivatives of these to find the marginal average revenue, marginal average cost, and marginal average profit, okay? So I'm going to make some quick notes here. So this is our marginal revenue, our marginal cost, be here. Go ahead and erase that. And our marginal, well, average profit rather, is 7.4 minus 0.03x minus 210 over x, okay? So now that we have all that down, we can find out what our marginal average profit would be. by just taking the derivative of taking the derivative of the average revenue. So the derivative of 12 is 0, and we have 0.04. Derivative of x is just 1. So we see that we have this. So what this is communicating to us is that the average marginal revenue is always decreasing at a rate of 0.04. So if we looked at that in dollars, we would say it's decreasing at a rate of 4 cents per whatever, or per unit, okay? If we go on to find the marginal average cost, we would need to take the derivative of here. And so, of course, we see this 210 divided by x. We could rewrite this, and I'm going to write it this way, as 210 x to the minus 1 plus, I'm going to go ahead and take the derivative of 4.6, which is 0, and go ahead and take the derivative of negative 0.01x, which is just minus 0.01, okay? And to finish this, we know that we have 210 as a constant, so I can pull that out. X to the minus 1 would be negative 1 times x to the minus 2 if we took the derivative of that. And then append on the minus 0.01 to that. And we end up with this. And if we put it back in the form that we had to begin with, this is what our marginal average cost would be, okay? Now for our last one. So we have this, okay? So for our last one, we would need to do what is going to be the marginal average profit. And of course, that would be the derivative of this, which should be the same thing as taking the derivative of this, or sorry. If we do this, which is the average marginal profit, so this will be the same as if we take the marginal average revenue minus the marginal average cost. But we can also take the derivative of this and get the same thing. I'm going to do it both ways to show you that we get the same thing no matter what. So first way that we can do this is just by writing out what this is going to be. So we have this minus, so we have the average marginal revenue minus average marginal cost. And so we see from here, this would be just minus 0.04. And this is minus, come here, write all that. And we distribute our negative. And if we do all that, we have our minus 0.04 plus 0.01 gives us a minus 0.03 plus 210 over x squared, okay? So that is one way to do it. I'll come over here now and show you that we could get the marginal average profit the same way by just taking the derivative of this, okay? So if we take the derivative of 7.4, that's 0. If we take the derivative of negative 0.03x, that gives us a minus 0.03. And of course, we know that 210 divided by x is the same as 210 times x raised to the minus 1. So if we take the derivative of that, that would be minus 210 times the negative 1, x to the negative 1 minus 1, which is a negative 2. And then this ends up being negative 0.03 plus 210 times x raised to the negative 2. And of course, if we rewrite that in the original way that we had our functions, we see we have this, and these are the exact same thing.